nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Okay, so let's get started. This is lecture 4 and for solid state devices, and today we'll be talking about solution of Schrodinger equation. Now there is quite a few topics to cover today, so we'll get started by talking about time independent Schrodinger equation, and we'll see how to frame the solution and understand the algorithm of solving the problems. So I'll take an example and show you how to solve it. The idea is not necessarily that we just focus on that problem per se, but understand the steps or algorithm of solving Schrodinger equation in general form. Now if you remember the original motivation of the problem, in lecture 1 and 2 we talked about the crystal structure, how to count atoms per centimeter cube, that is density. And we found this particular problem, that if we just take the number of electrons and multiply it with the number of atoms, number of electrons per atom, and multiply the density, that doesn't really explain the resistivity of a material. So resistivity of copper versus silicon, you wouldn't really be able to explain it. And what we realized from that discussion, that while all electrons are sort of created equal, but they do not behave equally, and that's understandable. You have heard about valence electrons, which sit very close to the core of the potential, and those of course don't go from hopping from one atom to another. But there are electrons higher up, which essentially can easily travel from one atom to another, and so therefore you understand that these electrons will not contribute equally to the conduction process, and that is exactly the problem that we are trying to solve. And here I am showing again the yellow circles representing the core of the atoms, the nucleus, let's say for silicon, and then on the right hand side the square potential bobbing up and down, that's a idealized representation of the Coulomb potential, because as you realize, and when the electron is close to the atom, the yellow one, the red circle which is supposed to be the electron, when it's close to the yellow one, then there is a lot of attraction because positive core and the negative electron. So the potential is low. So you can see the square going down. And when you're a little bit farther out, you are not as close, then the potential is somewhat higher. And you can see I have drawn the 3 positions of the electron. One is way down into the square, this periodic potential. You can see that that electron will essentially remain bound to that atom. They are not going to move. These are this 1s state, 2s states. Remember this from your high school chemistry. Those are the states. And I have again shown you one electron which is way up on the top. That essentially doesn't care about what this potential is. It's so far above the ground that essentially that potential variation will not mean much. And in between, of course, this will be a balance of the two. So we'll solve these problems and see how to, what energies the electrons, these respective electrons can sit here, and that will give us the information about how they contribute to the transport problem. So let's start by thinking about the Schrodinger equation. You remember in last class, we derived this simple second order differential equation. On the right hand side, I have the time dependent part, first derivative of time, and on the left hand side, we have a second derivative in terms of position. You realize that had it been a Maxwell's equation, the time derivative on the second right hand side would have been a second order equation. So Schrodinger equation is slightly different from the equation of light, and you will be doing a homework based on that. Now let's assume that we are just interested in time independent properties. We just don't suddenly turn things on, but let's say electrons are in steady state, you have applied a voltage, and the electrons are slowly flowing through from one contact to another. you want to know the time independent part. And one trick that people often use is to say that the entire wave function psi for the electrons can be decomposed into two parts. Just the position dependent part, psi of spec x, which is the small psi, and then the time dependent part is given by e to the power I et divided by h bar. So it's I omega t essentially. That's what you have there. So if I insert this equation insert this substitution on the left hand side, then you should be able to see that this is the result I will have. Do you see this? For example, on the left hand side, you can see when I take the second derivative with respect to position, and I'm not taking any derivative with respect to time, so that e to the power I et by h bar, that the whole thing will come out on the left hand side. And the same is true for u of x. But look at the right hand side, because I am taking a derivative with respect to time now. So therefore, I will pull out a IE divided by h bar in front. And as a result, you can see that this is a pretty simple substitution. And very quickly you can see that this exponential factor is the same both on left and right hand side. So I take it out, and once I take it out, it becomes this very simple equation, because all the e to the power exponential term, all of them are gone, and I have this simple equation. I can even simplify it a little bit more. Do you see how the simplifications have come about? I have cross multiplied 2m naught divided by h squared throughout with a minus sign. And therefore, the above equation, the equation on the top, becomes the last equation on the bottom. Now, one thing I will say before we start solving all the Schrodinger equation and other things, that many times, when you hear about quantum mechanics, people hear about all sorts of, complicated things, philosophically intrinsic things, that if his electron is here, where is the electron? If one electron is at a given point at a certain time, what happens to the fraction of the electron at some other time? And this set of probabilities and all sorts of popular literature you hear about. We are not going to just here discuss any of those things. For us, this is a simple second order differential equation. We'll learn how to solve it, how to use it, and be done with it. Of course, when you want to use quantum mechanics for your research and other things, you'll have to learn more. But those you will learn much more in your other courses. For this purpose, we'll just simply consider it second order differential equation. Very simple thing. Don't worry about the philosophical implication of quantum mechanics. That's for another course. Okay, so how do I solve this second order differential equation? Pretty simple, because if E, the energy E, and U is the potential, remember that the square potential going up and down. If E is greater than U, then the second term on the right is a positive, and I will call it K. I'll call by definition that whole thing, so that I don't have to write it over and over again. I'll call it K, and this equation becomes simply this. I mean, this equation we have solved million times before. And the solution is also well known, right? The solution is that generally it is A sine kx plus B cosine kx. Or if you wanted to write it in terms of exponentials, you can write it as A e to the power ikx plus e to the power minus ikx. And this, you know how this come about, this Euler relationship, you use them. You can go from one to another. That's it. So we'll remember this, right? Anytime we see an electron above the potential, we'll directly write this solution. Okay. What about the other case? Electrons cannot always be, yes, go ahead. No, it doesn't need to be a constant. If in this case, particular case, if U is a constant, then we'll assume K to be a constant. But in general, if U is a variable changing with position, in that case, we'll have to use numerical solution of the Schrodinger equation. And that we'll discuss towards the end of the class. Now, on the other hand, if the potential U, And I'll show you example how to use it. If the potential is larger than the energy, in that case, you immediately realize, looking at the top equation in the green box, that the second term will become negative. We'll call that thing, negative thing, alpha, just a name. And the solution of this equation, well, again, no rocket science necessary. The solution is e to the power minus alpha x plus e to the power plus alpha x. And you can easily insert it in the other equation and see that that solution is valid. So we'll use them often, as you will see. So I'm going to show you 5 steps of how to solve any time-independent Schrodinger equation. And those 5 steps are, first thing is somebody has to give you the U, the potential, how it's going up and down. Well, how will I get it? For example, if you think about silicon, right? Remember the crystal structure? Let's say you're going in along 1, 1, 1 direction, and you will encounter atoms at a certain gap, right? Certain spacing. So from that, you will get the value of the spacing of U. How will you get the depth of U? Well, remember, silicon has a certain number of protons. Some other material, let's say copper, will have some other number of protons. So therefore, depending on the material, that will give you the depth of the potential. So you will have to get it from someplace. That's what I'm saying. Once you have gotten in U and the boundary condition, I'll explain that in a second, you will solve the Schrodinger equation. Then, once you solve the Schrodinger equation, you will get the value of psi. You will interpret psi star as the probability of finding an electron at a given point. And then, once you have the small psi, you will multiply it with e to the power IET divided by h bar. Remember the time-dependent part? And get the whole psi, the large psi. And from that, you can see there are prescriptions for calculating momentum P or energy level E and all other things. Now, why did I get all this formula? Well, that is something you learn in quantum mechanics. For this, we'll just consider it as an algorithm. So let's solve some problems. Let's first solve a problem in which the one in the middle, in which the electron is such that it's not exactly on the bottom of the well, neither it is far away on the top. And that will give us some exercise of how to use the 5 rules that we just talked about. Now, the first thing you will notice in solution of these problems, that we will divide it. This will become clear as we go on, that we'll divide the potential, often in the periodic potential, into the 2 n regions, and that will give us n regions, and that will give us 2 unknowns. You'll understand in a second. We'll use the boundary conditions at plus and minus infinity. That will reduce the number by 2. And then we will use the continuity of the function and the derivative of the function to get 2n minus 2 equations. And then we'll take the determinant. And finally, we'll calculate the wave function. So let's see how it works. I mean, it looks like a very complicated thing, but you will realize in a second how it works. So let's think about this for a second. Assume, just for discussion, that the atoms are far away from each other. So far away that essentially they don't tunnel from one to the other. They essentially stay within their well. But at the same time, the well is not infinitely high. Well is finite, but the atoms are far away. In that case, I can just take one atom itself and solve the Schrodinger equation for that case. For example, I have shown on the top that if I take a box out of it, and that is what I have shown in the bottom as well, and I have reproduced it. The same one from the top, and I have reproduced it in the bottom. Now let's think about it, how to apply the solution methodology. So what was the step 1? Step 1 was that we'll have to solve the Schrodinger equation in various regions. I have 3 regions here. On the left, my energy is below U. Do you see? Because my energy is, U is, let's say at that point, a certain value. My electron energy is below that value. So my solution of that region will be, what should it be? Remember, anytime the energy is below U, then I'm supposed to have e to the power alpha x and e to the power minus alpha x. Remember, 5 minutes ago we just talked about. What about in the middle? In the middle now, the energy of the electron is higher than the local potential, because local potential, you can see, is much lower, right, compared to the electrons. As a result, what would be the solution? I could write it as a sine kx plus b cosine kx, or I could write it as e to the power ikx plus e to the power minus ikx. Either form would be fine. What about the right hand side? The right hand side, again, the energy U is greater than, the potential U is greater than energy E, so I have the same form. So 3 regions, 6 unknowns. So that was what I was saying in the last slide, that anytime you have n regions, you have 2 n unknowns. That was step 1. What about step 2? We said that we'll have to use boundary condition at plus infinity and at minus infinity. Then that will take care of 2 unknowns. Let's see whether we can work it out here. If you look on the right hand side for psi, then on the red, shown here in the red, you realize that the wave function probability of finding an electron far from where the atom is 0, right? And so the term with n e to the power plus alpha x, the n has to be 0, because if n is finite and if x is going to infinity, that term will blow up, and so that term cannot be a finite quantity. So n is 0. Now what about the blue side on the left? Because we know psi at minus infinity is also 0, right? We cannot find an electron either too far to the right of the atom or too far to the left of the atom. Now in this case, you have to be a little bit careful, because you see we are going in the minus direction. So instead of the C being 0, you can see in the blue region, the M will be now equal to 0. Do you see why? Because when I put minus x, that quantity is what begins to blow up if I don't set M equals 0. So these two are gone. You see, the boundary condition plus and minus infinity takes care of 2 unknowns. I am still left with 4, A, B, C, and D. What do I do about those? This is what I do about those. That next condition would be that between any pair of regions, you will have to use the continuity equation, a continuity relationship, that the wave function slightly to the left of the boundary and slightly to the right, that one must be the same, and so should be the derivative. Let's see whether we can use these 2 conditions to relate the 4 unknowns. Can we do that? So let's first look at the top blue regions, the 2 blue equations, and we'll talk about the red in a second. Look at x equals 0. If the solution or the wave function has to be continuous, then you can see that x will be equal to 0. So the left, right, just immediately to the left of 0, I have C, because x equals 0. What about on the slightly to the right of x? Which term will be 0? Well, you can realize that A has to be 0, right? Because that for x equals 0, that term is automatically 0, A sine x, and then B cosine x. Is this correct? That's right. And similarly, what about the derivative conditions? If you take the derivative first and then apply at x equals 0, you can see you will pick up a alpha c, e to the power alpha x, and you set x equals 0 there. And similarly, you take the derivative on the right hand side, and that gives you the equation, the second blue equations from the top. Well, I don't want to go through the next two equations, but you can easily see how it works. For example, the first red equation on the top, this is evaluated at x equals a, and at x equals a, the solution of the equation wave function is a sine ka plus b cosine ka, right? These two terms, and that must be equal to d e to the power alpha a, because you are evaluating at a. And similarly, the derivative boundary condition. Okay, this is no rocket science. You can easily see, match the wave function, match the derivative, be a little careful so that you put all the terms plus and minuses correctly. That's it. So how many unknowns I have? I have 4 unknowns and I have 4 equations. So I'm in a pretty good shape. I can solve this equation, right? So we will solve this equation. Of course, you can solve it in many ways, but if you remember matrix algebra, generally it's easy to solve it in this particular form. So for example, the C equals B, you can see how I have written it in the matrix form. In the matrix form, I have 1 and minus 1. You can see the vector A, B, C, D on the right hand side. And if you cross multiply, you will see that I have written the first equation on the top of the matrix is B minus C equals 0. That's what is the first equation. And you can read the other 4 equations from that easily. So you can see the term alpha and k, how they come about, with multiplied with A and C. And that's it. It's just a matrix form of the same equation. Now, how do you solve it? This equation, when you have 4 unknowns and 4 equations, you set the determinant of this thing to 0. So determinant of the previous matrix equal to 0, and that immediately gives you the solution of the equation in terms of tan of some quantity, and on the right hand side you have another function. Now, I have done 2 things. Oh, by the way, so let me, before I continue, you can see the only unknown in this equation, only unknown is E, because you can see the xi is E divided by u naught, but u naught you know, right? Remember the potential going up and down. So the value of u naught is given to you already. So in this equation, do you know A? You know A, right? The width of the potential. You know the value of A. So in fact, in this equation, you know everything except E. So by solving this equation, then you should be able to solve for the value of energy E at which electron is allowed to sit. Now, I did 2 things here, which I didn't really explain. And presumably you remember from your high school, or not probably in university undergraduate days, that why the determinant of a matrix is 0, and why, if when you set it in this particular form, this gives you the solution. I'll post a small note at the end of the lecture, or with the lectures in the website, that will explain this a little bit more in case you have forgotten. But this is essentially an algorithm of how to solve it. I'm not really explaining how the mechanical or mathematical aspect of it. Now, how do I solve this equation? This looks pretty bad. And how do I do it? Well, there are 2 ways. One is a modern way. You call a MATLAB function, and you will do it in your homework. Put that function in, and it will send you back the energy E for which the solution exists. Pretty simple. But many times in the older days, people use this graphical method, and that's very interesting. So let me explain how the graphical method works, because we will be using it later on also. Assume I want to solve this equation. X square equals x plus 6. Well, you could solve it in 5 seconds by taking the root of that, of the quadratic equation, right? You know how to solve this all. However, there's a very simple graphical way of solving it. Assume the left-hand side, I call it y1. y1 equals x squared. And the right-hand side, I call it y2. Let me plot now y1 and y2 as a function of x. So the blue, you can see, I have shown here the blue going up as x squared, y2 is x plus 5. So you can see that at x equals 0, the y-intercept is 5. Now the equation, these two pieces have to be equal to each other. Left hand equals right hand side. And therefore, the point they intersect is the solution. So it's a simple graphical way of quickly finding out where the solution is, right? Yes.
I know this is x plus 5 and x plus 6.
Certainly, certainly. Yes, yes. I should, exactly right. So the top equation should be x plus 5. Now, if you know that one, you can understand that process. You can easily see how the solution of this complicated equation would look like. So I have on the left-hand side tan of some quantity. That's a function of energy E through xi. I have just a function of energy E. So I could plot y1, and that is what I have plotted in red. The right-hand side, I have plotted in blue. And you can see this one when there is a particular value of xi. Do you see what value? At which the whole thing will go to infinity, plus and minus infinity. And from the top side, you can see when xi is equal to half, in that case, slightly from the left, it will become minus infinity. And slightly to the right, it will become plus infinity. Because when 2 xi minus 1 on the blue one, that when it becomes equal 0. So that's why this function has this strange form. Regardless, you can see the solution is when the red line crosses the blue line. That's the solution. And that one, I will rotate it a little bit, because remember the solution I'm looking for is the energy E, right? That's the solution. So my solution is really in the x-axis. So if I just rotate this 90 degrees, then I can easily read off that energy E, and that's where the electron sits in the quantum well. At energy E, it will sit there. Why it cannot sit below, or neither can it sit above, right? So that is where the energy will sit, and you can easily calculate it graphically. You can see that as soon as the potential is given and the value of A is given, you can draw the blue and the red proportions, and that immediately gives you the value of the bound level. Okay, it's nothing complicated here. So I know how to calculate the energy level where electrons sit. Now, most of the time that should be sufficient, but sometimes I would also want to know the wave function itself. For most transport problem, you will see that we will not need this additional information, but if you needed it, one thing you realize that this A, B, C, and D, if I somehow know that magnitude, then I would know the value of psi completely. But given that this matrix multiplied by the vector is equal to 0, of course, these are not linearly independent. And so there is no way I can get 4 values out of this. What I can, however, do is get the value of B, C, and D, any 3, in terms of the remaining one. How would I do that? Well, think about this submatrix A minus 1, 0 alpha, and cosine kx. Let's take it down. And remember, that's the submatrix that multiply B, C, and D, right? And anything that is left out, I take it to the right-hand side. Do you see? Let's talk about the second equation, for example, 0 alpha 0. Now in 0 alpha 0, when I write out the equation, you will see the first term was Ka on the left hand side. Do you see in the second line K and A? And you will see that K multiplied by A on the bottom equation, I've taken to the right hand side with a minus sign. Do you see that? And similarly, the other ones, you can easily do the other ones. Now, you don't have to take one submatrix. You could take any other submatrices. It will be fine. I took here B, C, and D, but you can see that after I solve it, which is invert this matrix, then I will get B, C, and D in terms of A. And also, of course, there is this alpha and K, but remember the alpha and K depends on U, and energy E, but I just solved energy E in the previous slide, right? So in fact, I know alpha, I know K, I know the whole thing, except for A, I know B, C, and D values exactly, right? Okay. Now, how do I get the value of A? Well, that brings me to the last slide on this topic. Remember that I had said that you have to find electrons somewhere. You know, either it's sitting in the middle, or to the right, or to the left, but between plus and minus infinity, it will sit somewhere. And the probability of finding an electron is psi squared. And so what I have done is integrated between infinity to minus infinity and set it equal to 1. And now you can see I have 4 unknowns, of course, C, A, B, and D. 4 unknowns, that's good. But remember, I have just solved B, C, and D using A, in terms of A. So once I'm done with all this, put this all in, what is the only unknown? Is A is the only unknown. And if A is the only unknown, I can set it equal to 1, and I'm done. And as soon as I know A, I know B, C, and D, and I have solved the whole problem. You see? So this is the process, 5 steps. This is the process. If you remember, you cannot go wrong. You'll solve all the problems exactly in the same way. Now, sometimes there are, remember this was the electron I said, is somewhere in between. It's not too deep in the well, not too far out, but sometimes the electron is, if it's really in the core, like 1s atoms, right? 1s electrons, very close to the core. In that case, a further simplification is possible. So for example, for the infinite quantum well, you can again solve for the middle region as A sine kx plus B cosine kx, that's fine. But the left and right side, remember where you had e to the power alpha x and e to the power minus alpha x, the potential is so big that e to the power alpha x, that will decay so fast that essentially I can think the wave function is 0 on the left and 0 on the right, right? It's so big that e to the power alpha is very big, and so it decays so fast that I might as well consider the wave function going to 0. So that simplifies my life, because I can say that psi at x equals 0 is 0, because I cannot find an electron to the left of the well. It's so high, potential is so high. And similarly at x equals a, which is the other side of the potential, I can also say, well, electron cannot possibly go to the neighbor in between the potentials. And once I solve these two equations, I can find the energy levels for these bound states. And the energy levels is given by h square n square and pi square 2 m naught a squared. I hope you will check it out. This is a simple solution. Check this out. I will not go through this, but this one is interesting. Do you remember how did the energy level in the hydrogen go as a function of n? Do you remember that when I said ENM equals constant bracket of 1 divided by n square, remember, minus 1 divided by m square. Remember, it goes as 1 over n squared as you're going higher and higher in energy. They get closer and closer together. Look at this one. So that was a 3-dimensional hydrogen atom. Look at this one. This one is a 1-dimensional square potential, and here the separations are going more and more because it is going as n squared. So the first level is at 0.1 eV, second one will be at 0.4 eV, next n equals 2. The next one will be at 0.9 eV because n is 3, n square is 9, so 9 times the first level. So you can see the difference between the two. So these 5 steps that I talked about, if you follow them, you cannot possibly go wrong. But if you try to take shortcut, then what will happen that you will solve some problems fine, but often you might get stuck. If I give you a slightly complicated problem, then you might get stuck. Follow the rules, you will be fine. And this problem, you might think that this is not a very recent problem. After all this have been discussed about 100 years ago. Actually not. This is a paper I took from Science is a very prestigious journal from 2006. Here people are talking about if you have silicon and then you put the silver on top of it, then you can use the same formulation I talked about a few minutes ago to calculate where the electrons sit. Now, I have not explained where the potential diagram comes from. By the end of the course, you will be able to solve all this problem. But for now, what I want you to focus on is this. Look at the rate potential. You can see there is a region equal to a square potential sort of, and also a triangular region. You can see the various levels at 1, 2, 3, 4, and 5. And you can see the energy levels are not getting separated as n squared because this is not a rectangular quantum well. The triangular region is widening, and so it doesn't follow the previous rule, of course. But this is a problem one can solve analytically. It's a very easy problem to solve, and presumably, I'm not sure, I may have assigned a homework on this. So you can take a look. But another problem, which anybody who are using this computer today, I mean, all of your computer, essentially suffers or not suffers, is based on this principle on the right-hand figure. I told you about silicon dioxide. Remember that amorphous region and silicon, the well-ordered region, and I had 3 regions, remember? Silicon dioxide, and polycrystalline. Do you remember from before? And in that case also, what we'll see that between silicon and silicon dioxide, to the right-hand side, you have a potential well, shown here almost like a parabolic structure, and again, you have these bound levels. And you will solve it exactly the same way I told you about, that you will get this potential and then follow the rules, and you will get these bound levels. And in fact, this is very important. That tells you how many electrons there are available for conduction, and as a result, you can calculate whether your Pentium is going to have a certain speed or not, right? So these problems are not theoretical problems, very practical day-to-day problems. Okay, so we'll talk briefly about bound versus tunneling states. So this has been the last topic. I have solved 2 cases already, right? When the electron is inside this potential going up and down, when it's very on the below, in the bottom case, intermediate case. What about when the electron is far up? In that case, how will I solve the problem? Well, I can solve the problem in a particular way. You remember that in this case, E is always greater than the potential U, right? Always. And moreover, this is so far up that I do not even see the potential variation too much. It is like when you are in the aeroplane and trying to look down on the building. Whether the building is going down by 500 feet up and down, when you are in 35,000 feet or 45,000 feet, you don't really care. You can assume that the land is flat and then solve for the problem. So here, I'll assume U to be essentially equal to 0 because I'm so far up. And if I assume U to be 0 for a particular value of energy E, I can easily solve this problem. Sine kx plus cosine kx, or the other form, which is a little bit easier to do, e to the power ikx, or minus e to the power minus ikx. You know, these 2 solutions. Now, the positive going wave, if you are just thinking about electron moving to the right, I can easily assign it to the e to the power ikx. Remember that when you solve for the wave equations in 604 in electromagnetics, the plane wave moving to the positive direction is e to the power ikx, and correspondingly anything that is going to the left hand side is e to the power minus ikx. Okay, so I have these 2 electrons and I am essentially done with my solution. That's it, this is my solution. But now the problem is, how do I get the value of A plus and A minus, and whether there are additional issues associated with it. So I will get the value of the Schrodinger equation in a similar way, and if I wanted to calculate momentum, you can see that if I insert a e to the power ikx, use this relationship psi star, how do I get psi star? So if I have a function e to the power ikx, what will be the psi star? E to the power minus ikx. This is simply the complex conjugate. If I insert it in here, you can see that the momentum will show that if I e to the power plus ikx, moving to the right, if it's e to the power minus ikx, moving to the left, right? From this expression. Now let's come down from the lofty height to somewhere a little closer to the ground, still above the potential, but not way up, so I can see the variation. In this case, of course, I can see the variation. So in these three regions that I have, remember that anytime I have n region, I'll have to solve individual functions in these three regions, in this n regions. So I have these three regions, so I write the solution in these respective three regions. But the distinction is that now all three regions are above the potential. So therefore, my solutions are all e to the power ikx and e to the power minus ikx form, right? So I have those three solutions. Now let's say the electron is coming from the left. Electron is coming from the left. What will happen that in the first interface at x equals 0, a fraction of them will get reflected, a fraction of them will get transmitted, just like light. When you have light coming from one side, on let's say incident on glass, a fraction of gets reflected and a fraction get transmitted. Similarly, on the next surface, similarly a fraction will get reflected, a fraction will get transmitted. But what about the right hand side? Once it gets transmitted, right, then it's not going to come back. It's going to keep going because there's nothing reflecting it back, right, to the right hand side, if it is coming from the left. If it is never comes back, then what should be the value of n? Because it is not coming back. So the value of n has to be 0 because it is supposed to be the component which comes back. You see, had you started from the right hand side, then in that case the value of c should have been 0, because once it starts going to the left, it is not going to come back, right? So depending on the situation, you will take one of them out, and correspondingly you will match the boundary conditions, right, at x equals 0 and x equals a. But now you have a problem, because if you match the boundary conditions at each interface, you have two interfaces, you will get 4 equations. How many unknowns do you have here? You have 5 unknowns here. Remember, in the previous case, I had psi equals 0 at infinity and psi equals 0 at minus infinity. Took care of 2 of the boundary conditions. Here, I have been able to take out just 1. And therefore, I am left, I cannot solve this problem exactly, right? I cannot have an eigenvalue problem. And so there is no bound levels, no eigenvalues, because I cannot set the determinant equal to 0 with 5 unknowns. And what I can do, the maximum I can do, is to express everything in terms of 1 unknown. You know, just I keep 1 and then I express everything else in terms of that unknown. And that is the maximum I can do. And again, this is a problem, and this you'll do an homework on it. You know, all this seems a little abstract unless you sit down and solve a particular problem. You will do problems in MATLAB and also in NanoHub. So this all will become clear at that point. But the point is that, again, this is a huge problem in terms of understanding how semiconductor devices work, and we'll see that later on. These days, the laptop gets very hot, right? You put it in lap, and it's really, you have to, even in Walmart, you can buy these coolers so that it doesn't get as hot. The reason it gets so hot is because there is a lot of current tunneling out from every individual transistors. So it is as if it is leaking, every transistor is leaking a little. that leaking process is essentially exactly this tunneling process. So if you have this potential, but on the right, let's say, on the right-hand side, there's nothing reflecting the electrons back. So if you have certain number of electrons on one side, in the silicon side, that electron can get out, exactly using the formulation I just talked about, and as a result, you can have tunneling current. That's what makes the laptop hot. And so the things that you are learning here in terms of being able to solve that problem, electron coming from one side, going away and not coming back, is a very important practical problem. And that's something we'll look at. Now, these again, by the third part of the course, we will cover all this and how to calculate the magnitude. But the homework in between asks you to solve the tunneling coefficient and the tunneling current for a structure like this. And you will do that in home. So I will conclude here. What we have discussed is the solution of Schrodinger equation. Now, these are analytical solution, and as I mentioned, that in this one, the way we have solved this particular problem, it assumes that the potential is piecewise constant. So that in a given region, I can write the solution either in terms of sin x, cosine x, or in terms of e to the power alpha x plus e to the power minus alpha x if the energy is below. And in this piecewise region, constant region, then I stitch things up, stitch the solutions up at every boundary, and then use the boundary condition plus infinity and minus infinity to pull them everything together. Remember, psi square equals 1. That helps me to also pin down the wave function. So eigenvalues, where the electrons sit, and the wave functions, all those come out. Now, if it is more complicated, it's varying up and down all the time, then of course you cannot use this analytical method. Computers are much better than us in solving that type of problem. I will show you in the beginning of next class that the continuation of this lecture is how to solve the problem numerically, and you will also solve the problem numerically in your homework. But given those two, numerical and analytical, you are in good shape. Any potential you are given, any potential, you can always calculate where the electrons will sit, whether they are moving at a certain velocity or not, and as a result, how they contribute to the conduction process, you see. So that's the goal we are going for. This is all intermediate steps. And what we will do in the next class and the class after is to solve the real problem, which is, you see here I took one atom and tried to see where the electrons sit. Of course, it's not one atom. These are series of atoms, 10 to the power, let's say 8 atoms, all in a line. I'll have to solve that problem, and that is something we'll see probably 1 or 2 classes from now. Now, what I mentioned so far is that most of the solutions we do are all analytical solutions because it's easy to do in the class. And this is how historically things had been done, because in old days, I'm talking about 1940s, they didn't have a big computer like you do. So in that case, doing analytical work is the only right way of approaching the problem. But these days, of course, we have computers, and therefore we can solve many more complicated problems. And I want to show you how to solve the Schrodinger equation, not analytically. Remember the 5 steps we had about putting boundary conditions and matching. It's not that, but numerically how to solve it on your computer so that you can solve complicated problems quickly. Consider I have a complicated band. The ux is not piecewise constant, becoming a rectangle up and down. After all, that was an idealization. Now the question is, how would you solve the Schrodinger equation in this particular case? You can see that this could be complicated in principle, analytically at least, because you can see if you look at the k values, sometimes the energy level E is above U, so k is greater than 0. Sometimes it is below 0, so the k is there's a decaying solution, and in general a complicated mess. how do I solve for these things? This is how to do it, and you will do it in the second homework yourself as well. Assume first that you have a ux, the potential ux. Somebody has given it to you. It may come from the atoms themselves or the molecules that you are thinking about, and in some way this reflects all the other electrons that you have except the electron that you are thinking about. All the other electrons, the protons and everybody, the core net potential is given in this blue curve ux. Let's divide the space of this in x space, let's say 1 dimension, into n plus 1 points. So let's say the whole dimension distance is 20 angstrom, and let's say I divide it in 20 pieces. So each piece is about an angstrom. I can do that, and you can immediately see that therefore I can specify that at that point, at that node, what the potential is. Let's say it's 3.1 eV, and the next one, let's say 2.8 eV, and so on and so forth. I can specify that. Now let me assume that although I do not know the solution of this equation, but whatever the solution is, I just sketch it out in the rate curve, and whatever it is, of course I can write that value to be in the third node as psi 3 or psi 1, psi 2, psi 3. These are still unknowns to me. But of course, in principle, I could say that I know the values at this point. If I do, then you can see this is very easy because it's a continuous function, the rate curve. It is very easy to relate psi 3 to its two neighbors, psi 2 and psi 4. How? By simply Taylor series expansion, and this is how. That let's say x naught is the third node point. X naught plus a is the fourth node point, and I could easily expand the solution because it's a continuous curve in terms of the fourth node point, in terms of the third node point, and you know the Taylor series expansion. The first derivative multiplied by a, the second derivative multiplied by a square over 2. A is the lattice spacing, or I have sometimes used p. So it's the same thing. I could relate the third one to the solution of the second one. I do not know them values, but I could always write it. Now, if I do a sum, you see something very nice will happen, because when I do the sum, then you can see that the sum on the left hand side is obvious, but the first derivative, because they have opposite sign, they will disappear, right? But the second derivative, which has the same sign, they will come down very nicely, which is on the right hand side, a square and the second derivative of psi at x at the node 3. So if I want to evaluate the second derivative of a function at a point, I'm just taking the two neighbors and essentially constructing the second derivative from there. Okay. Now, in general, therefore, for any node I, if I wanted to evaluate the second derivative, I could just use the information from the two neighbors, divide by the lattice spacing squared, and I'm done. So now you see, this I could write. I've written the same Schrodinger equation, except there is this term T naught to capture the h square over 2 m naught a square. That's the initial part. Remember, these are free electron mass. We're not talking about effective mass here. And the second derivative, well, I could write it in that form, just a derived. And so when I insert that second derivative in the first equation, you can easily see for the ith node, it will connect the solution from the two neighbors and it will have the corresponding form. Now remember how many points I have. I had the whole thing gridded up in n plus 1 points. And so therefore, in principle, I should have n equations, every one connecting the two person on the left and person on the right. And so you connect the whole thing up, and then you have the solution. And so this is just one. So you'll have a series of equations. Now this is, of course, if you try to do it on a pencil and paper, this would be horrible, but the computers are not as smart or do not get as bored, so they can solve the problem easily. I have the equations. N unknowns, of course, the psi values are the unknowns. But remember, I have to put the boundary condition, right? on minus infinity and plus infinity. Now, of course, in computer, there's no minus infinity and plus infinity. You should take some value on the left and on the right, and then move it a little bit to see your original solution doesn't change. If it doesn't change, as far as you're concerned, that's plus infinity, that's minus infinity. And I'll set this to equal to 0. And once I set them to equal to 0, I can write this equation. So that's the equation for any node. That's the equation for the first node, but fortunately, I already know that psi naught is 0. So that's gone. That's good. So I just need to know about the neighbor on the one side. And similarly, on the other side, that was gone. And the whole equation, set of equations, I can write it as a matrix, n by n matrix, that's the H. They call it Hamiltonian. And then you can solve this eigenvalue problem. And when you solve the eigenvalue problem, you have all the energies, right? Now, how many eigenvalue will I have? A quick thing. Equal to the number of node points, because, you know, it's an n by n matrix. So I should have n eigenvalues, which is good. There's a lot. That's one. And second is, remember how this is connected with what you did before. Remember setting the determinant to 0, right? What I did over there is took the e on the other side. So in our case, it was h minus e multiplied by psi equals 0. And we said the h minus e, the determinant of that equal to 0. Setting the determinant of that equal to 0 is exactly the same as finding the eigenvalue of a problem. So therefore, these two procedures are exactly equivalent. I'm just following that 5 steps, remember? Just exactly the 5 steps in a numerical form here. So I have, let's say, 20 levels. I'm very happy, and I bring it to my professor by solving MATLAB, or, you know, you have the NanoHub tools and all those. Very impressed, but it turns out the professor says that you know how to program, but you don't know how to the physics. And this is why. Remember the equation of a solution of a Schrodinger equation. The first level, it was like a half sinusoidal curve, right? In the second one, it was 2 humps, one going up, another going down. So each of the solutions actually had a certain number of nodes. The first one, 0 node, the second one, 1, 0 crossing, and so on and so forth. Now think about the 20th one. The 20th one will have 19 0 crossing, let's say, going up and down, let's say. Now, of course, that will have a lot of energy. It's really going up and down very fast. And that's way up there. Now, when the energy is way up there on the top, remember my boundary condition. My wave function was supposed to go to 0 at minus infinity and plus infinity. Think about the wave function on the top that you have just calculated. Of course, for that one, it is not going to 0. In computer, it is going to 0 because you put by hand a hard boundary where you said wave function has to be 0 on that first node. So what has happened in that process in the computer, what you just did, you didn't not only solve this potential, but on x equals 0, you put an infinite potential up, forcing the wave function to be 0. Therefore, all these spurious solutions above you came about because you put an artificial boundary condition. What will happen that if you change the boundary a little bit, the ones in the bottom will not change, right? Because for them, that left boundary was really infinity. But on the top, because the square potential, as soon as you move it a little bit, all those will keep changing. Those are not physical boundary solutions. So you have to get rid of them all. So being able to take a big supercomputer and solving a big problem doesn't mean that you always get the right result. You have to think about the physics first, and only then you are going to get the right results. Okay? So let me end with this. This was the extra material for, I guess, lecture 4, and we will continue then on the energy band and other issues in the next lecture. Thank you.